Hello, everyone. So, in this lecture, we are going to mostly focus on studying the hydrostatic forces, and in particular, we are going to solve some examples for you in order to determine the pressure at these different kind of problems, as well as also introduce barometers. And so in this lecture and also in the next lecture, so we are going to solve different types of calculations for kind of determining the magnitude and location of the hydrostatic force on different objects. And this will be very important for kind of designing curved surfaces, channels, dams, and other things, because you need to know these hydrostatic force as well in order to be able to design those kind of structures. So first, let's get started with this example, with a simple example. Determine the pressure at the oil water interface and at the bottom of the tank. Okay. So I'm gonna draw the figure for this oil water interface, but before that, I just want to mention that we're gonna use the same principles and formula that we learned before. So we talked about the theory in the last lecture, and now we are gonna use it in applied cases, different applications, and specifically using this formula, hydrostatic distribution formula, which is a very important formula for incompressible fluids, as we learned before, which are at rest. Okay, so this is the focus of our course here. So let's draw the figure. How does this look like? What we are gonna try to calculate. This tank of water, you have something like this. I'm trying to draw it. Okay. And here we have this tank. So this tank is filled with two material. So water is at the bottom of that. So we have water here. And then on top of that, we have oil. So I'm just gonna write it down up to this point, and here is free surface. So this length is 1 meter. This one is 3 meters. This length is 2 meter. And from here to here is 1 meter. Okay? So, the density of oil is also given as 881 kilogram per meter cube. The density of water is also given as 1,000 kilogram per meter cube. And the atmospheric pressure, or P0 at ATM, which means atmospheric pressure, is 10 to the 5 Pascal. Okay. So now the question asks me to find the pressure at the oil-water, first at the oil-water interface, means here. And then second, at the bottom of the tank, which means here, okay, anywhere here. So one thing we know from previous lecture is that the only important parameter here is the depth, right, in the fluid. For a fluid at rest and an incompressible fluid at rest, we know that the pressure only depends on Z, or the elevation. And if you move horizontally from any point to another one, the pressure does not change. What does that mean? That means that the pressure here and here are equal, right? The pressure here and here are equal along the same horizontal lines, okay? So the only thing I need to know is the depth, which I am kind of considering for calculation. So let's get started to solve this, and I'm going to use this formula here, which is for finding the pressures at different points. So solution or answer. So this is the formula we have. P, or pressure, equals to rho G H plus P0. Right? P2 is what? So for here, for any point, for example, P1 or P2, the pressure is going to be, and here the pressure we know, here the pressure is going to be P0, right? At this surface, it's a free surface. So, for example, P1 or P2 or any of them is going to be rho GH, the height of the fluid, plus atmospheric pressure P0. Okay? So let's first start at the interface. So at the interface, which is going to be P1, we can write P1 or interface is what we have here. We just have to look at, for example, you are here or any point, it doesn't matter. You have oil on top of you, and then so you have this much oil in top of you, and it's only the depth that matters. And then you have the atmosphere here. So you have two fluids on top of you, right? So I'm just gonna write rho, the density of oil, times G, times the depth of the oil on top of this point, right? So let me write it again. So I'm gonna have rho oil G times the depth of the oil on top of point 1, or the interface, which is gonna be 1 plus 2 plus 3, right? So it's gonna be 1 plus 2 plus 3, and then this plus the atmospheric pressure, which is P0 or P naught. Okay, so this is going to be the pressure at the interface. So let's now see let's now plug all the numbers we have. So it's going to be, let me just open it again. Okay, so let me just plug the numbers. So I'm gonna have the density of oil, which is 888, so the P1, P interface equals to 881 times G, which is 9.81, times 1 plus 2 plus 3 is going to be 6, plus P0, which is 10 to the 5 Pascal. And if you add all of them, we are going to get 5.1 times 10 to the 4 plus 10 times 10 to the 4. So finally, we are going to get 1.51 times 10 to the 5 Pascal. And just so you know, again, 1 Pascal is 1 Newton per meter square. Is the SI unit. And then now let's look at the bottom of the tank. What would be the pressure there? Okay. So we are gonna calculate P2, or bottom. Is gonna be what? Based on this formula we had, is gonna be rho g z2 minus z1 plus P2, which is gonna be, here is the other way. So we are gonna have this rho g of water plus the P at here, right? So I'm just gonna write it down. So it's gonna be P interface, P1 interface, plus, and now on top of this, we have water, right? on top of here, we have water. So we have to add the rho GH of water. This is very important. You should make sure which fluid you are looking at when you are adding this pressure, okay? So on top of this point of 2, we have water, so we are gonna add this one, and then we are gonna add it to the pressure at P1 that we had already calculated, okay? So what do I mean by this is P1 interface plus rho water times G times how many meters? 1 meter. Right? Because we have 1 meter on top of that. So this is very important to know that we have here rho water and here we have rho oil, right? Because we had oil here in this area, while here we had water. Okay, so if we calculate it, we are gonna get 1.5 times 10 to the 5, which is the P1 interface. I just wrote it from here. Plus rho water. Rho water is 1,000. Times G times 1. So it's going to be 0.98 times 10 to the power 4. And then if you add these two together, we are going to get 1.6 times 10 to the 5 Pascal. Just plug the numbers in to this formula. Okay, so this is how you can calculate the pressure at different fluid interfaces just by using this formula, this hydrostatic distribution. Okay. So now I want to talk about hydraulic jacks, about this idea. What is the idea behind hydraulic jacks that you might have heard of? So the next topic is hydraulic jacks. So these jacks also work based on this requirement of equality of pressure principle. Okay, so they work based on the required equality of pressure principle. So let's see how do they work. And we can do that based on this just a simple pressure definition which we learned. So the way these jacks work is that you have two different areas, okay? So say let me try it here. Okay, and then Okay, so you have please still here. And one area here. And these two areas are different. Okay. So we have two cross section, one A1 and the other one is A2. Okay. And we need to have the same pressure in both of these, right? So if you have any say fluid here, so like oil or any other type of fluid, say within these two sections, okay. So any type of fluid, we need, if they are on the same, because they are on the same depth, right? We need them to have the same pressure, because so the same depth, as you see, if for example you have this coordinate system and this is z, they are on the same z, right? They have the same depths. If you look at it here, so the same depths means that P1, the pressure at point 1, should equal to pressure at point 2, right? So this means that, what is the definition of pressure? The definition of pressure is F1, the force. So this is the force, for example, that is exerted. We exerted a small force at F1. And then we have another force that is acting on cross-section area 2. Okay. So because of the same depths, we have pressures should be equal, and thus we can just write what is the definition of pressure here is going to be F1, the force that acts on cross-section 1 over A1. Okay. And then you can add the, if you want, the atmospheric pressure, but you can also neglect it, equals to the pressure at 2, which is the force acting on it, over A2 plus P0, again the atmospheric pressure. These two are going to cancel out, and so that's why we typically don't write it, because they are going to cancel out. They act on all the objects. So this means F2 is going to be A2 over A1 times F1. So what does this mean? This means if you design a jack that the A2 cross-section is much bigger than A1, and that is how the jacks work, then this means that here, this is going to be much bigger than 1. And so F2 should be much greater than F1. So with a small force at A1, a large force at the larger piston will be developed. So this is the main mechanism of hydraulic jacks, right? So they have two different cross sections, and then based on the required equality of pressure principle, you can apply a small force at F1, and because of these different cross sections, you are going to gain a very large force, a larger force at F2, right? So with a small force here, you're going to get a much larger force at F2, right? So this is just using a very simple pressure equality principle based on the depths that we learned. Okay. And now I want to introduce barometers. These are some devices for measuring atmospheric pressure. So barometer. A mercury barometer is used to measure the atmospheric pressure. Okay. Let's see how it works. So here we have mercury inside this box. And there is a reason we have mercury and not water. And we are gonna discuss that for measuring atmospheric pressure. Okay, so the mercury comes up to here. So this is mercury here. mercury. And here we have vapor pressure, some vapor here, so we have a vapor pressure that acts here. And then this length is h. And then on top of this, we have atmospheric pressure. Which we call it P0, okay? So this device is, or this instrument is used to kind of measure the atmospheric pressure, okay? So let's see how it does that. So if you write this pressure equation that we learned for fluids, P1 equals to rho gz2 minus C1 plus P2, we are going to get atmospheric pressure. So I am going to start from here, just for this point. I'm going to write it from two sides, because this is a fluid. If we move horizontally, the pressure is not going to change, okay? So I'm just going to write it first here, and I'm going to call this point A, and then I'm going to write it here and going to call this point B, right? And because they are on the same depth, right, with respect to if this is z direction, they are on the same depth, so their pressure should equal, okay? So I'm just going to write it down. So P at A should equal to P at B, same depth or elevation. So what is P at A? P at A is just P at atmospheric pressure, or P0, right? And P at B, I can write it from here on top of that. So I have P vapor plus rho of mercury G times H, right? So I have mercury here, and then I have this vapor pressure here, right? So this is how you can get it. And because P vapor, this vapor pressure is very small, it's almost zero, we can approximately write that the P of the atmospheric pressure equals to rho mercury GH, right? This is an approximation. And now I want to say why we are not using, and then I want to say why we are not using water instead of mercury. So here we say P atmosphere is going to be almost equal to rho mercury GH mercury. Okay. So if you do this for the standard atmospheric pressure, the mercury, the depth of mercury or H is gonna be around 76 centimeter. So it's less than 1 meter, around I would say 2.5 feet. Okay. So just 2.5 feet, about 76 centimeter. And why we didn't use water? Why we don't use water to measure atmospheric pressure? So the question is, what if we used water instead of mercury to measure the atmospheric pressure, or P-atm. So if we use that, so this is gonna give us about 10 to the 5 Pascal, okay? The P atmosphere, as we know, is about 10 to the 5 Pascal. So I'm gonna write it 10 to the 5 is gonna be around rho water G H water. Okay. So instead of raw water, I'm just gonna write it down, the density, which is 1000 kilogram per meter cube. And so if you calculate it, and this is around 10, H water, the depth of water in this case would be around how much? It's gonna be around 10 meters. So we cannot really, we can do it, but you need 10 meters, a 10 meter instrument to be able to measure the atmospheric pressure with water. But if you use mercury, because its density is much higher, then you will only need 76 centimeter instrument or tube. Okay, that's why we don't use water here and we use mercury. So therefore, the atmospheric pressure is equivalent to the pressure of a 10 meter column of water. So this is very important concept that you need to know. If you don't remember the atmospheric pressure, you can just imagine a 10 meter column of water, okay? 10 meter column of water. So the pressure that you feel at the bottom of that 10 meter column of water, okay, so if you are here, this pressure that you feel is equivalent to the pressure of free atmosphere, the whole atmosphere, okay? So if you, for example, if there is a pool and then you go to a pool, swimming pool, which has like a 10 meter or let's say 12 meter depth, and then you go here and there is like 10 meter water on top of you. Okay, so you are gonna feel, the pressure that you're gonna feel is approximately 2 times the pressure of the atmosphere, the atmospheric pressure, right? Because this is gonna be the atmospheric pressure equivalent to atmospheric pressure. And then you also have the atmospheric pressure on top of that acts on this free surface, right? So the 10-meter column of water is equivalent to the atmospheric pressure that we feel. Okay, so this is very important concept, and you can simply calculate the atmospheric pressure if you forget how much it is. So it is just 10-meter column of water. So rho water GH is gonna give us the pressure. So rho of water, you should all know, it's 1,000 kilogram per meter cube. Times G, say it is 10 meter per second square. And then we have H, which is 10 meter. So it's going to be around 10 to the 5 Pascal or Newton per meter square. Right? So this is how you can calculate the atmospheric pressure. Okay, and barometer is used for this type of calculations and measurements. Okay, so now in this lecture I'm gonna divide it to 3 sections, and in the next section I am going to talk about U-tube manometer, then solve some examples of that, and after that we are gonna talk about hydrostatic forces on a plane, okay, on an inclined plane, and then we are gonna solve some examples of that as well.